Hello everyone. It is my honor to present our work, ChatScratch, an AI-augmented system toward autonomous visual programming learning for children aged 6 to 12. As computational thinking education and programming reach younger age groups, platforms like Scratch are facing new challenges. Firstly, primary school children frequently lack the proficiency required for digital programming platforms, facing hurdles in literacy, arithmetics, fine motor skills, and hand-eye coordinations. Secondly, the prevailing educational approaches are still dependent on close mentoring from professional educators and a well-structured curriculum. This often leaves children from underprivileged area and community struggling to access the resources and guidance they need. By assembling block-based code, Scratch allows children to engage in creative programming, present their work in multimedia forms such as games, animations, and stories. To see how we could help children learn and play with Scratch, we conducted a formative investigation with 6 experienced Scratch educators. We participated in their in-person classes and conducted a one-on-one interview to discuss the potential difficulties children encounter while engaged in creative programming with Scratch. As a result, we report 3 main challenges. Firstly, children frequently get stuck, encountering an artist block, which is a temporary creative impasse where they struggle to progress with idea during the project planning phase. Secondly, the existing options for assets creation with Scratch constrain children's creative expression, leading to a form of unbounded creativity. Finally, the cognitive skills required for code implementation surpass the capability of children in their formal operational period, leaving them uncertain about where to start. To overcome these challenges and support children's personally meaningful Scratch learning, we introduced ChatScratch. During the project preparation phase, ChatScratch leveraged the interactive storyboard with visual cues as inspirations to overcome artist block, enhancing both the detail and richness of their projects. When creating assets, ChatScratch incorporates stable diffusions with ControlNet, enable children to craft high-quality, tailored assets using image polish. As children embark on the coding phase, ChatScratch proposes a Scratch-specialized large language model to address their coding queries through voice interface. Through voice-guided code assistant, children are directed to find the required code blocks, enhancing their proficiency with code over time. By generating editable code template to the script area, it offers a tangible start point, guiding young learners to produce high-quality code. We help children detail and enrich their project with visual cues for asset creation. First, children can start with a certain need. For example, they can draw a simple doodle of cat and tell, "My character is a cat," to the system. In response, the system will display 4 refined concept images on the canvas, which is a cat reading with glasses, a skateboarding cat in casual wear, a cat in a pirate hat on the ship, and a cat in ship attire. Second, we address the need for children to enrich their project. For example, they might say, "I have no idea about the next character." Children can then click on these displayed images to hear the explanation, including a basic descriptions of the new element and how it related to the existing element in the project. We proposed a large language model specialized for Scratch to achieve our code assistant. In the Scratch community, Scratch cards stand out as introductory materials for programming. To select high-quality examples from Scratch cards, 3 educators with more than 4 years of teaching experience were hired to work with the team. The selected cards are utilized as structured knowledge for in-context learning. Based on the Scratch specialized large language model, ChatScratch offers a step-by-step guidance strategy. By typing on the voice bubble, children can hear the suggestion on code block categories and how to use them. If they still got problems, in the second step, they can click the Unclear button. By hitting the appeared code help button, the system automatically generates a basic executable code templates within the script area. Children can freely adjust it, use the template as a scaffold to craft interesting personal projects. We conducted a within-subject study involving 24 children to test our system. Each child used both Scratch and our ChatScratch to complete creative programming tasks. All participants were programming novice with less than 1 year of experience, aged between 6 and 12. To mitigate potential time-related and carryover effects, we implemented a counterbalanced design concerning the project theme and the tool used, along with a 48 hours interval between the two tests. This means that some children start with ChatScratch, while others begin with Scratch, and the theme were randomly assigned as well. Each test session lasted about 70 minutes, including time to familiarize with the system, take breaks, and work on the project. Through this comparison, we aim to address 3 key research questions related to our objectives. We ask, how ChatScratch supports creative tasks, high-quality code implementations, and the autonomous creation of personally meaningful projects in Scratch programming. To answer these questions, we examined 7 key metrics. First, to assess support for creativity, we employed the visual element count to gauge assess richness, expert ratings for assess originality, consistency, creativity, and quality, and the CSI questionnaires to evaluate system usability. Second, to evaluate the quality of code produced, we used the Dr. Scratch score to measure computational thinking performance and examined the code retention and expansion to see how children utilized and built upon the provided code template. Finally, we analyzed the video recordings of tests and interviews to understand how ChatScratch supports the development of personally meaningful projects. Looking into our data, we observed a significant increase in originality, consistency, and creativity among the assets created with our ChatScratch. These findings suggested that with the aid of visual cues and image enhancement, children are able to create more freely and produce assets that closely match their expectations, thereby enhancing their overall creative expression. Additionally, we observed a performance closely matched in terms of quality, confirming that assets produced with ChatScratch are of a quality comparable to those from Scratch's built-in library. We also evaluated children's subjective perception of the creative support they received. Overall, children had a positive view of both systems, with ChatScratch receiving higher evaluation across all 6 dimensions. The collaborative support provided by ChatScratch better represents children's efforts in creative tasks. Visual cues assist children in exploring the richness and details of the project, while image enhancement elevates the inconvenience associated with acquiring original assets, allowing children to concentrate more on the creative process. By evaluating the level of computational thinking, we observed an increase in their total score from 13.2 to 18.1. This improvement indicates a progression from a basic to nearly a master level within the framework of Dr. Scratch assessment. Additionally, we observed significant improvement in 6 dimensions, with the exception of flow control. In the second analysis, code retention evaluates the effectiveness and usability of the code produced by our assistant, focusing on the extent to which children adopted the provided code suggestions. The average retention score of 0.74 illustrates that about 3/4 of our suggested code was retained by the children. Through expansion, we highlighted that the improvement in the code quality is not solely due to the code we provided. The children's own efforts are also crucial. Consequently, the final project shows that more than half of the final code was further developed by the children, with an expansion score of 0.54. Finally, we attribute the support of personally meaningful projects to the facilitation of an iterative creation process and the incorporation of personal preference through our ChatScratch system. Overall, we conducted a systematic formative investigation to identify the central barriers that hinder children's autonomous learning in Scratch. We introduced ChatScratch, which, by leveraging visual cues, image enhancement, and code assistance, empower children to craft personally meaningful projects. Furthermore, we organized a comparative study between Scratch and ChatScratch, employing both quantitative and qualitative methods to demonstrate ChatScratch's effectiveness in supporting creativity, code implementations, and the creation of personally meaningful projects.